Let's discover stacks. Stacks follows the LIFO ordering principle, which stands for last in, first out. That means that the last inserted item will be the first item to be removed. We can think of a stack of books, where we can only add a new book at the top of the stack. This is called pushing onto the stack. We can only take a book from the top of the stack. This is called popping from the stack. And finally, we can only read the cover of the last element of the stack. This is called picking from the stack. Stacks have a lot of uses, such as the undo functionality in a word processor. We can push onto the stack each keystroke the user types. When the user makes a mistake and wants to undo it, we pop the last inserted keystroke from the stack. Another use is a symbol checker that checks the correctness of the parentheses, square brackets, and curly braces in a program. When we find an opening symbol, we push it into the stack, and when we find a closing symbol, we check if it matches with the opening symbol located on the top of the stack, popping it if it does. In a similar way, stacks can be used for function calls. We can store the block of memory associated with the invocation of a function and pop it after the execution of the function ends. Stacks can be implemented using singly linked lists. As we previously learned, linked lists have nodes. Let's recall the node class. It has two attributes, data and next. Data contains the value for the node, and next points to the next node. Now we will implement a class for the stack. The stack will have an attribute called top that will store the last inserted node in the stack. Initially, the top node will be none. To push a new element onto the stack, we will implement the push method. First, we need to create a new node with the data. If the stack is not empty, the next node of the new node will be the top node. Finally, whether the stack was empty or had elements, the top node will be the new node. To pop an element from the stack, we can implement the following method, which will also return the value of the deleted item. If the stack is empty, we will return none because there is no data. If the stack has elements, the popped node will be the top node. The new top node will be the next node of the top node, and the popped node will point to none. Finally, we will return the data of the popped node. The last method is pick, which returns the data of the last element of the stack, but does not alter the stack. If the stack has elements, we return the data, and if it is empty, we return none. Instead of creating a stack from scratch each time, we can leverage the LifoQueue class from Python's Queue module. LifoQueue behaves like a stack. This is not to be confused with queues, a different type of data structure. After importing queue, we can create a new LifoQueue with a max size. If max size is 0, the stack will be infinite. We can add elements using the put method, get the size of the stack using the queueSize method, pop elements from the stack using get, which also returns the popped element, and check if the stack is empty, among other functionalities. Let's practice.